Okay, in the last class, we discussed the symmetry-adapted linear combination of atomic orbitals, and we applied that knowledge then to the construction of the molecular orbital diagram of the water molecule. So today, I would like to do another example before we are moving over to the next chapter, which will be about acid and base concepts. So first, let us think about how to construct the molecular orbital diagram of NH3 using the concept of symmetry-adapted linear combination of atomic orbitals. So what are the first steps to do? Well, I have to be clear about the point group. And the NH3 molecule is pyramidal molecule, belongs to the point group C3V. So the next step is that we define the axes. And one useful way to define the axes is to let the x-axis point to the right and the z-axis pointing to the top. Then the xz plane is the paper plane, and the y-axis that stands perpendicular. We can orient the NH3 molecule along the z-axis and have one NH1, this one here, being located in the xz plane. So that defines the coordinate system. What is the next step to do? Well, we have to be clear about what is the central atom of the molecule and what are the ligand atoms. That's easy to decide. The central atom will be the nitrogen atom, and the three ligand atoms will be the three hydrogen atoms. So next we have to think about, well, what are the valence orbitals of the ligand atoms that we want to use to construct ligand group orbitals from. For hydrogen atoms, choice is simple. We will just choose the three hydrogen atoms. So the three valence orbitals of the hydrogen atoms for the construction of the ligand group orbitals. So how many ligand group orbitals will we get? Well, the number ligand group orbitals is equal to the number of atomic orbitals, and therefore there will be three ligand group orbitals. So what is the next step? The next step is we need to determine the reducible representation for these ligand group orbitals. We can use the orbital swapping method to do that. So you need to go through the symmetry operations step by step and decide whether the symmetry operations swap the orbitals or not. If they're getting swapped, then they get the character 0. If they stay at their position, they get the character 1. So for the identity, well, all three orbitals will change in their position. Therefore, each one will get the character 1. And the sum of these three characters 1 then gives the first character in our reduced representation, lambda. So secondly, we need to look at the C3 symmetry operations. We only need to look at one of the two, so we could either choose the C31 or the C32. That wouldn't matter. But regardless what we do, we see that when we carry out the C3 symmetry operation, that all three orbitals change their positions. So that means that all three orbitals get the character 0. And well, 3 times 0, well, that's 0, and that gives us the second character in our reduced representation. Last but not least, we need to look at the vertical mirror planes. So the overall 3, we could choose either of one. So for instance, we can choose the one that stands here, bisecting this one is up here. Now, how many orbitals are getting swapped in this case, and how many do stay at their position? Well, you see that Well, this orbital here stays at this position, but these two here, they're getting swapped up. That means now that this orbital here gets the character 1, and these two orbitals here get the character 0. Now, when we sum that up, then that gives 0 plus 0 plus 1, and that gives 1, and that gives the last character in our reducible representation. So now we have fully determined our reducible representation, which has the characters 3, 0, and 1. What is the next step now? The next step now is to determine the irreducible representations for the ligand group orbitals. That will determine the symmetry types. And we can use the reduction formula in order to do this. So we can start, for instance, with the symmetry type A1. So how many ligand group orbitals will have the symmetry type A1? Well, that is 1 over the order of the point group. So in this case, the order of the point group is 6. Why is this? Because we have 6 symmetry operations to consider. You can read this from the character table. We have the identity, we have 2 C3 operations, and we have 3 sigma V operations. So that gives overall 6 operations. Okay. So then we have to form these products here for all the symmetry operations. The number of operations in the class for the identity, that is 1. Okay, that is this one here, times the character of the reducible representation. That is the character we determined on the previous slide. So that was 3. Okay, and times the character of the irreducible representation. Well, this is this character here, which is 1, plus now the respective product for the C3. So that's 2 for the number of operations in the class, because we have now 2 C3 operations to consider, times 0, which is the character of the reducible representation for the C3 symmetry operations that we determined previously, times the character of the irreducible representation, which is now this character here underneath C3 for A1, and that's 1, so it's 2 times 0 times 1. So we have to add to that the respective product for the sigma B. So what is this? Well, in this case, the number of operations in the class is 3, because we have 3 sigma V mirror planes. The character of the reducible representation is 1. We saw that previously on the previous slide. And the character of the irreducible representation is also 1. So that's this one here. So now that gives 3 plus 0 plus 3. Well, that gives 6. And 6 over 6, well, that gives 1. And that means that the character of the number of the ligand group orbitals that have symmetry type A1 is 1. So now we can do the same also with the next symmetry type, A2, and we would find that the number of ligand group orbitals of this symmetry type is 0. Okay? It's not explicitly calculated here, but I'm just telling you that. Last but not least, we need to look at the E-symmetry type, and let's do the calculation here explicitly again. So that's again 1 over 6 times the product for the identity, which is 1 times 3 times 2, because we have 1 operation in the class. The character of our reducible representation is 3, and the character of the irreducible representation is 2. Now this is this 2 here. Okay. So we have to add to that the product for the C3. So we have 2 operations in the class. So that's this 2. and the character of our reducible representation was 0. Now the character, the irreducible representation is 1, so this is this one here. So to that we have to add this product. So the number of operations in the class is 3, because we have 3 sigma v's. The character of the reducible representation is 1, and the character of the irreducible representation is 0. So that's this 0 here. Okay. Now when you calculate this, then this is 6 plus 0. 6 plus 0 plus 0. Well, that gives 6, and 6 over 6, well, that gives 1. Okay. So now at first glance, it looks like we are missing one ligand group orbital, because previously we said that we have 3 ligand group orbitals. And well, 1 plus 1, well, that gives only 2 ligand group orbitals. However, we need to consider now that this symmetry type, the symmetry E, is double degenerate. And when it's double degenerate, then this number 1 actually means 2. And it means that we have 2 double degenerate ligand group orbitals, both having the symmetry E. So overall, we have 1 ligand group orbital that has the symmetry type A1, and 2 ligand group orbitals, which are double degenerate, that have the symmetry type E. Okay, now we have determined the symmetry types of our ligand group orbitals. Next, we need to determine the symmetry type of the central atoms. So first of all, central atom orbitals. So first of all, we need to be clear what orbitals we want to consider. So these are the valence orbitals of the respective atom. So we have a nitrogen atom to consider here, and a nitrogen atom has the 2s and the 2p orbitals as the valence orbitals. So which symmetry types do they have? Well, to determine this, we can simply look into the character table. So the 2s orbital has A1 symmetry, because s orbitals of central atoms always have the totally symmetric symmetry types. That's the one listed in the first row of the character table. Okay, so this is A1, all characters are +1. So now what about the 2p z and the 2px and the 2py? Well, we see that the 2px and 2py are listed here. So they have the symmetry type E, and you see that they are written in parentheses. X and Y are written in parentheses, and that means that they are double degenerate in this point group. So last but not least, we have the 2pz orbital. So the letter Z here is in the row for the symmetry type A1, and that means that our 2pz orbital will have the symmetry type A1. So, and now we can combine orbitals of the same symmetry type to form molecular orbitals. Okay, so next step, we determine which group orbitals and settling orbitals of the same symmetry type. Okay, so now the orbitals of the same symmetry type must be combined to form MO. If an orbital has no partner, again, then it's non-bonded. Same thing we saw for the H2O molecule, the same procedure that we're going through again. Okay, now for the symmetry type A1, we have seen that the 2s and the 2pz orbitals of the nitrogen have that symmetry type, and that our first ligand group orbital has also that A1 symmetry type. So how many molecular orbitals will we get? Well, we always get the same number. So when we have 3 orbitals to combine, then we will get 3 molecular orbitals as a result. So now for the A2 symmetry, we don't have any central atom orbitals. We also do not have any ligand group orbitals. So for that reason, we also do not get any molecular orbitals. For the symmetry type E, we see that we have the 2px and the 2py, and we have the second and the third little group orbitals. So now we see that we combine overall 4 orbitals to form molecular orbitals. And therefore we will get how many molecular orbitals? Well, we will get 4 molecular orbitals. Now, because we have combined doubly degenerate orbitals with each other, the 4 molecular orbitals must also be doubly degenerate. Okay, and that means that we will form 2 doubly degenerate bonding molecular orbitals and 2 doubly degenerate interbonding molecular orbitals. This information is included in that symmetry type, and it's very helpful to construct molecular orbitals in the following. All right, so let's do this. Let's construct the molecular orbital dying for NH3. So the first step is always write an arrow and label it E. For energy, so we construct the molecular orbitals according to energy. So we write the central atom on the left side here and the ligand atoms here on the right side. So in the next step, we write down the central atom orbitals according to energy and label them with their respective symmetry type. So there is the 2s, which needs to be energetically lower than the 2p, and the 2p orbitals all need to be written with the same energy. We know that they have the symmetry type A1 and E respectively. So on the right-hand side, we will have the hydrogens and the ligand group orbitals coming from the hydrogens. So one of them is the A1 symmetry, and the other 2 have E symmetry. So the E orbitals have actually slightly higher energy than the A1 orbital. But if you don't know that, that's okay. You can also write them all with the same energy. We could again find that out if we considered more closely how many nodes these orbitals have, which we will not actually do. Okay, then we have all our ligand group orbitals. We have all our atomic orbitals. Now, let us combine the orbitals to form molecular orbitals. So we have 3 A1s, so we have to produce 3 A1 type molecular orbitals. Again, qualitatively, you can estimate that when you have 3 molecular orbitals, that one will be bonding, that one will be interbonding, and one will be approximately non-bonding, could be slightly bonding or interbonding, we don't know that. But the bonding one is low energy, the interbonding one has high energy. You have to write the bonding one below the atomic orbital, which has the lowest energy, which is in this case the 2s. So that's important. You have to write the interbonding one above the A1, well, ligand group orbital or atomic orbital, highest energy, which is in this case this one. So don't write them any differently. So this, the third one, the approximate non-bonding one, you can write about halfway in between the 1A1 and the 3A1. So then you're done with the A1. Yeah, you should label them 1, 2, 3 respectively according to energy. Then you're really finished. You should also connect the 3 molecular orbitals with the atomic orbitals from which they have been constructed from using dotted lines. Okay, so now the next step, we need to go to the E orbitals. So we have two 2p orbitals that have E-symmetry and two ligand group orbitals that have E-symmetry. Now, as I said before, that means that we get two orbitals of E-type, which are bonding and which are doubly degenerate. So we have to write them with exactly the same energy into the molecular orbital diagram. If you don't, then that's actually a mistake and you're losing points. And you have to write another pair of anti-bonding molecular orbitals of the type E that have a higher energy. Again, you need to write these here below the atomic orbital, which has the lowest energy, which in this case, these two p orbitals, and that anti-bonding pair above the orbitals that have the highest energy, which in this case, these two ligand group orbitals. Okay, you may suspect that this bonding pair here has a higher energy than this bonding molecular orbital, because this bonding molecular orbital has an influence from the energetically low 2s, while these two have only influence from the energetically relatively high 2p. So you may suspect, therefore, that these orbitals here have a higher energy than that orbital, but the energy is lower than the energy of this orbital here, because this is approximately non-bonding, while this one here is still bonding. Okay. You may also suspect that these two orbitals here have an energy which is higher than this one, because this one still has an influence from the energetically low 2s. These two only have influence from the 2p, but you couldn't say with 100% certainty that these two would be higher than this one without an exact quantum mechanical calculation, which we won't do here now. We'll only construct molecular orbital diagrams qualitatively. Here. So again, you should connect the molecular orbitals with the atomic orbitals from which they have been made using dotted lines, as you can see here. So now we see we have constructed all of our molecular orbitals. There's no other symmetry type to consider, but we still need to fill the electrons into the molecular orbitals. So now, how many electrons do we need to consider? Well, the nitrogen has 5 valence electrons. 2 are in the 2s, and 3 are in the 2p. The 3 hydrogens have 1 electron each, so that gives overall 3 electrons. So that means that we overall have 8, and we have to fill them now according to energy into the molecular orbitals. So that fills this A1 with the first 2. That fills the first 1e. It fills the second 1e. Now we have 6. Finally, we will have also this molecular orbital. So that gives us 8 electrons. And this 2A1 orbital here is the so-called highest occupied molecular orbital. This 3A1 here is the so-called lowest unoccupied molecular orbital. This means that our molecular orbital diagram is now complete. It's again insightful to compare the molecular orbital diagram with the simple Lewis dot structure of NH3 to see similarities and differences. So according to this simple valence bond structure here, there are 6 bonding electrons in these 3 NH bonds. Is that confirmed by molecular orbital theory? And the answer is yes, because we have here these 6 electrons in these 3 bonding molecular orbitals. However, you also see that the molecular orbital diagram provides finer details. We can see from here that these two electrons are actually energetically lower than these four. So this is not an information that we would get from the valence bond picture where all the bonding electrons appear equivalent. So lastly, we have here this electron lone pair at N, which doesn't participate in the bonding, so it appears as non-bonding electron. Can we see this in the molecular orbital diagram too? The answer is yes, because this 2A1 we said before is an approximately non-bonding molecular orbital. Okay, so this is what I wanted to say about the molecular orbital theory. At this point, we will revisit molecular orbital theory when we apply it to coordination chemistry, and then we will get to know also more complex examples of molecular orbital diagrams. But for now, as an introduction, that shall be enough. And we will now start a new chapter, which is about acid-base concepts that are relevant for coordination chemistry. And there are two acid-base concepts which I will cover in more detail. That's the Lewis acid and base concept, and I will present that Lewis acid and base concept from the perspective of molecular orbital theory. And then we will talk about another concept in more detail, which is the hard and soft acid and base concept. So first of all, a brief review of the Lewis acid and base concept. So it was developed by Gilbert Lewis. And what is the definition of a Lewis acid and the Lewis base? Well, do you remember this? What is a Lewis acid and what is a Lewis base? Can anybody tell me? You may unmute yourself.
A Lewis acid, they're an electron pair acceptor and a base is a donor.
Correct. So a Lewis acid is an electron pair acceptor, and a Lewis base is an electron pair donor. All right, then what is a Lewis acid base reaction? Well, it's a reaction in which, well, the Lewis base donates an electron pair to the Lewis acid. However, this is not a complete transfer of that electron pair, otherwise it would be redox reaction. There will only be partial transfer to form a covalent bond, which is called a dative covalent bond. So for instance, a BH3 molecule is a Lewis acid. It has only 6 electrons surrounding the bond, so it doesn't obey the octet rule. So it would like to accept another electron pair. Whereas an NH3 molecule is a Lewis base, it has an electron lone pair that it can donate. Okay, so when we have a Lewis acid base reaction between these two, well, this electron lone pair will be donated to the bond here in a way that shares this electron pair here, which was formerly the nitrogen, between the nitrogen and the boron. Okay, we call this kind of bond so-called dative covalent bond. And in order to indicate this, we write this covalent bond not as a simple line, but as an arrow that points from the donor to the acceptor, indicating that this bond is a dative bond. However, fundamentally, there is no difference between a regular covalent bond, in which basically the two partners contribute one electron each, and a dative covalent bond, in which one partner contributes 2 electrons and the other partner doesn't. This is only a matter of perspective, but sometimes this perspective is, well, instructional to understand the way the respective molecule has been formed. So the reaction product between Lewis acid and Lewis base is called an adduct. Okay, it's also called a Lewis acid base adduct, and there's a dative bond that holds that adduct together. So the Lewis acid base concept is very powerful. It's the most general Lewis acid base concept. It also includes Bronsted acids, Arrhenius acids and bases, and it can even explain ionic crystals in a way. So let us look at a few examples that shall illustrate this. So for instance, we can conceive the reaction between an H plus and an OH minus ion to form H2O as a Bronsted acid base reaction. Okay? So in this case, the OH minus ion would be the proton acceptor, and the H plus would be the proton donor. It donates itself to the OH minus ion to form the water molecule. Of course, that also would be an Arrhenius type of acid base reaction, but we can also view it as a Lewis acid base reaction, because we can say that the OH minus ion donates an electron pair to the H plus, which accepts that electron pair to make a covalent bond. Okay? And in this way, the OH bond would be viewed as a dative covalent bond. Okay, so the other OH bond would be viewed as a regular covalent bond. However, of course, there's no actual difference between this bond here and that bond here. Okay, it just makes sense to view this bond here in this case as a dative bond, just because of the way the bond has been formed. Okay, but fundamentally, these two bonds are, of course, exactly the same. Okay, we also can explain coordination compound between metals and ligands using this concept. You will hear a lot more later about this. We will hear a lot more about this later in this course. So for instance, zinc 2 plus can react with 4 hydroxide ions to form tetrahydroxozincate 2 minus. It is a coordination compound in which OH minus ions coordinate to zinc 2 plus. And of course, we can describe this as a Lewis acid base reaction. In this case, the OH minus ions again would be the base, the zinc 2 plus ions would be the acid. So the OH minus ions would donate an electron pair to the zinc and make a dative oxygen zinc bond. Okay, so only one is illustrated here, but in this complex here, of course, there would be 4 such dative bonds. You can even explain ionic crystals this way. So, for example, when you have a reaction between calcium 2 plus and 2 hydroxide ions to form calcium hydroxide, which would just precipitate out of your solution, then you can view this as a Lewis acid base reaction if you want to. You can say, well, during that reaction, we will have here this electron lone pair of the OH minus ions that will coordinate to the calcium 2 plus, which will act as Lewis acid, to make a dative bond, even though this dative bond may be a very polar dative bond, which is close to an ionic bond, but we have discussed previously that a 100% ionic bonding is actually never possible because of finite electronegativity differences because of finite energy difference between orbitals. Okay, now let us look closer at the Lewis acid and base concept from the molecular orbital theory perspective. Okay. So according to molecular orbital theory, Lewis base is a Lewis base when the associated molecule has an approximately non-bonding highest occupied molecular orbital. And the Lewis acid is a Lewis acid when the respective molecule has an approximately non-bonding lowest unoccupied molecular orbital. So how can we understand this? So let us first look at the Lewis bases. So for instance, as we saw before, the NH3 molecule has a Lewis base, and you can see here the molecular orbital diagram again of the ammonia molecule. So now we see that the highest occupied molecular orbital in the ammonia molecule is an approximately non-bonding molecular orbital. Okay? It was the second molecular orbital of the symmetry type A1. So now why is this situation ideal for this molecule to act as a Lewis base? Okay. So first of all, of course, we have to have an occupied molecular orbital, otherwise the electrons couldn't be donated. So what if the highest occupied molecular orbital, so now the highest occupied molecular orbital is always the orbital with the highest energy electrons. So therefore, these electrons will be most easily donated to a partner. So now, why is the non-bonding situation for that HOMO ideal? Well, if the HOMO was anti-bonding, then that HOMO would likely be so high in energy so that the electrons would be completely transferred to a reaction partner. And in this case, you would not get a Lewis acid base reaction anymore, you would get a redox reaction. If that HOMO here was a bonding molecular orbital, then the energy of these electrons would likely be so low so that no thermodynamic driving force for electron transfer would happen, and these two electrons would just remain completely non-bonding. So therefore, the non-bonding HOMO is ideal. The energy of the electrons is high enough so that a partial electron transfer can take place, but also low enough so that a sufficient reactivity is achieved. Okay, so now what about the Lewis acids? So for instance, BEH2 is a molecule which is linear, in which is a typical Lewis acid. So as such, it should have a lowest unoccupied molecular orbital, which is approximately non-bonding. We can briefly construct the molecular orbital diagram of the BH2 molecule to verify that. So the BH2 molecule belongs to the point group D infinite H. So the character table for D infinite H is a bit unusual because you have the infinite principal axis and you have an infinite number of C2 axes in addition, and also an infinite number of Moore planes. So therefore the character table is more difficult to understand. I do not want to go into the details here. I just wanted to mention that because of these infinities, we have symmetry types that you haven't discussed before. So we have the 2s orbital having the sigma g plus symmetry type. So that's the totally symmetric symmetry type in this point group. And the 2p orbitals have sigma EU plus and pi U symmetry respectively. So for the hydrogen, we have two ligand group orbitals. One of them has the symmetry type sigma G plus, and the other one has the symmetry type sigma sigma U. Yeah, there must be a plus missing here. So there needs to be a plus here. Okay, so now we can again combine orbitals of the same symmetry type. So we combine this sigma G plus here with this sigma G plus. So that forms a bonding molecular orbital and an interbonding molecular orbital. And we can combine this sigma U plus 2p orbital with the other ligand group orbital, which has sigma U plus symmetry, to form this 1 sigma U and this 2 sigma U. That also has to be plus. Orbital. So now I see that these pi U to p orbitals remain non-bonding, and you can write them like this into the molecular orbital diagram. It's the same energy. You fill in your electrons. The barium has 2 valence electrons. The hydrogens have 1 electron each. So that's overall 4 electrons. And while the first 2 will have to go into 1 sigma G plus, and the second 2 will go into the 1 sigma U plus. So this makes this orbital here the highest occupied molecular orbital. And you see in this case, the highest occupied molecular orbital is a bonding orbital. Okay, so for that reason, you wouldn't expect that the BH2 molecule acts as a Lewis base. Rather than that, it acts as a Lewis acid, because you see that the lowest unoccupied molecular orbitals are non-bonding. So again, why is that situation ideal for the molecule to act as a Lewis acid? Well, the LUMOS are the lowest unoccupied molecular orbitals. So these are the molecular orbitals into which electrons can be donated most easily to stabilize these electrons. But if these orbitals were bonding, they would be energetically so low so that the electrons would be completely transferred from the partner and you would get a redox reaction. If they were interbonding, then they would be so high so that they could unlikely find a partner that could still donate these electrons into the orbital, and in this case, the molecule would remain unreactive. So again, the non-bonding situation for the LUMOS is ideal. All right. So let us see in the following. What the nature of the dative bond is, depending on the relative energies of the HOMO of the donor and the LUMO of the acceptor. So we will have here two molecules, A and B, generalized, where A will be the donor and B will be the acceptor. So now, let us choose the following case, which is that the HOMO of the LUMO will be, so the HOMO of the donor will be equal in energy to the LUMO of the acceptor. Okay. So now in this case, you will form a perfectly covalent bond in between the donor and the acceptor. And the electrons will be completely equally shared between the donor and the acceptor, and there will be no polarization of that dative covalent bond in between the two species. However, we go to another case in which now the HOMO of the donor is slightly higher than the LUMO of the acceptor. Then we can still form a bonding and interbonding molecular orbital in between them. But now that electron pair, which gets donated from the donor, will not be completely equally shared anymore between the donor and the acceptor. Because that bonding molecular orbital, the electrons in it, will be close in energy to the LUMO of the acceptor. It will be located primarily at the acceptor. And that refers to a dative covalent bond which is now polarized, and it's polarized toward the acceptor. So we have a polar covalent bond that is polarized toward the acceptor. Okay, so now we can make the energy differences even larger. So now the HOMO of the donor is much larger than the LUMO of the acceptor. Now in this case, we can still form a bonding molecular orbital and an interbonding molecular orbital. But now that bonding molecular orbital is almost completely localized at B. And that means that we have effectively transferred the electrons from the donor to the acceptor completely. And that means that we do not have a Lewis acid base reaction anymore, but we have oxidized donor A and reduced acceptor B, and we have a redox reaction leading to an ionic bond. Okay, so we have no Lewis acid base reaction, but a redox reaction. So now there are more cases to consider. We can also consider a case in which the LUMO of the acceptor is somewhat higher than the HOMO of the donor. So now again, you can form a molecular bonding molecular or interbonding molecular orbital through the interaction of the two. Now you see that the bonding molecular orbital will be energetic closer to the HOMO of the donor A. For that reason, it will be localized primarily at the donor A, and we will have a covalent bond, a dative covalent bond, which is now polarized toward the donor A. The electron density will primarily, but not exclusively, at A. Okay, then we can move the orbitals of B even higher to the extent that now the HOMO of B is energetically closer to the LUMO of A. Okay, so now in this case, you will get an interaction primarily between the LUMO of A and the HOMO of B, and for that reason, the B will now act as donor and A will act as the acceptor, and the electrons in the HOMO of A will remain unreacted. They could only interact with the LUMO of B, but because the energy difference is so large, there will be hardly any covalent interaction. Okay. So if you move the orbitals of p even higher, okay, then eventually again the HOMO of p will be so much higher in energy than the LUMO of A, so that the electrons here will be completely transferred to A, and so A gets reduced and B gets oxidized. We're not getting a Lewis acid-base reaction anymore, but we're getting a redox reaction. So A gets reduced and B gets oxidized. Okay, then let us stop at this point.